This activates the intracellular protein called AKT. And in the scheme of insulin signaling, AKT is the protein that makes the magic happen. AKT is the protein that stimulates all of the effects of insulin. These effects we will discuss in the next video. Last video we went over insulin signaling in a pretty in-depth fashion. But let's take a step back and look at all of the effects that occur upon insulin binding to its receptor and the insulin signaling being carried out properly. The insulin receptor is essentially found everywhere within the body, including the brain, heart, thyroid, pancreas, fat, muscle, liver, intestinal tract, lung, blood vessels, gallbladder, red blood cells, white blood cells, and eyes. We'll look at two examples very in depth, and then take a broader view of all of the other functions of insulin. Likely the most important function of insulin is to increase glucose uptake. In our cells, we have this small vesicle called a GLUT4 containing vesicle. You can essentially think of it like a small package containing GLUT4 receptors. These are receptors that are typically on the surface of our cells and have the capacity to take glucose out of the bloodstream and transport it into our cells. However, in the absence of insulin signaling, these GLUT4 receptors are allocated to the vesicle contained inside the cells and guarded by a protein called AS160. In this state, the GLUT4 vesicles cannot fuse into the membrane of our cells and allow glucose to enter. But after insulin activates AKT, AKT can then phosphorylate AS160, allowing this protein to essentially detach from the vesicle containing the GLUT4 vesicles, allowing these vesicles to fuse to the membrane of our cells and begin uptaking glucose. This is the mechanism by which insulin stimulates glucose uptake. Similarly, we have a protein inside of our cells called GSK3, which inhibits the synthesis of glycogen, which is simply just a long chain of glucose stored within our cells that we can subsequently break down and use the glucose as energy. Insulin, by activating AKT, can essentially stop this protein from inhibiting glycogen synthesis. In a roundabout way, by inhibiting the protein that is stopping us from synthesizing glycogen, insulin increases the synthesis of glycogen. In a little less detail, insulin stimulates the uptake and storage of fatty acids. Insulin also stimulates the uptake of amino acids into skeletal muscle, as well as the synthesis of muscle and body proteins. In this way, insulin is an anabolic hormone. Insulin inhibits the breakdown of glycogen, as well as we discussed, the synthesis of glycogen. Insulin inhibits lipolysis, which is the breakdown of fat, and increases triglyceride production and storage. Insulin also inhibits muscle protein breakdown. Insulin works in the brain to stimulate brain growth and is vital for necessary cognitive functioning, as well as modulating the production of neurotransmitters and the receptors for these neurotransmitters, mitochondrial function, and the synthesis of cholesterol within the brain. And a disruption of insulin action within the brain leads to the impairment of neuronal functioning and the capacity for the brain to change. For example, insulin increases the production of serotonin and alters dopamine turnover. And the absence of insulin or insulin resistance within the brain induces anxiety and depressive-like behaviors. Insulin can stimulate the production of glutathione, one of, if not the most important antioxidants within the body for decreasing inflammation and allowing us to detoxify foreign substances such as pesticides, heavy metals, and medicines. Insulin can increase the number of LDL receptors within the body, therefore decreasing blood levels of LDL, meaning that inadequate insulin functioning may actually increase our risk of cardiovascular disease. Within the immune system, insulin can be anti-inflammatory as well as strengthen the immune system, meaning proper insulin signaling has a major impact on disease trajectory and the ability to fight against diseases. Unbeknownst to many, insulin also decreases hunger and increases thermogenesis, therefore increasing energy expenditure. And overall, proper insulin signaling has the capacity to reduce food intake and increase energy expenditure. When it comes to steroid hormones, insulin increases the production of steroid hormones like testosterone, as well as decreasing the production of SHBG, which is a protein that can bind to free hormones and make them less accessible to our cells. We also see that insulin stimulates nitric oxide production, a protein that allows for the vasodilation of blood vessels and improves systemic blood flow. Insulin has roles within the kidney to increase sodium, potassium, and water reabsorption, allowing us to properly recycle water and electrolytes. And finally, insulin is important for thyroid functioning, as it can increase the number of thyroid receptors and the proper functioning of these receptors. Therefore, insulin can augment thyroid hormone signaling, one of the potential mechanisms by which insulin can increase energy expenditure. As you can tell, there are a lot of functions of insulin, and when people call insulin the fat storage hormone, or dwindle its functions down to a very simplistic form, it undermines all of the fascinating physiological functions of insulin. In the next video, we'll talk about insulin resistance, what it is and what causes it.